Hello friends, सबको नमस्ते. So today in this video we will create a object detection furniture object detection model, and for that we use SSD. Okay, so let's get started. So before the explanation, please like, share on my video. Okay, so this is a Roboflow library which we have to install to download a model, download a dataset from Roboflow. So this is a dataset. Let me run it. Okay, the format which we are downloading is Euro v9. Okay, but we are using SSD model here. Stick time, please wait. Completed. So here this is a furniture data set. Okay, before opening, let me rename it. I want to rename it, so that's why I've used os.rename. Old name from furniture to we convert that name into furniture detection data set. Okay, let me run it now. So let me refresh it. So it's converted. Now let me see how many classes which we have. For that, let me open it. It's taking time, so please wait. So we have to open this data.yml file. So these are the classes which we have: chair, sofa, and table. Okay, we will use this. These are the classes which we use for object furniture detection. So now these are the libraries which we used. These are three libraries which you already know. Let me explain you why we import Torchvision. So we import Torchvision because provide dataset model architecture like SSD, fast RCN, and this for download the architecture we use Torchvision, Torchvision. Then you import data loaders, which is required to have load data in batches. Then we require transformation for data augmentation or any resizer to convert that image into tensor format. And we these are the classification hat which we have imported here for SSD. Okay, these are the utils which is internal utility function which have some internal utility function, box matching and loss helper. Okay, then this is weight file which we have imported. This is a weight file which we are using, SSD 300 bg16 weight which we are using here. And let's get started. Here, see why we are creating the class here. First, the reason of creating the class is that customer class is created to load image and their corresponding annotation files, convert them into tensor, and return them into a format that PyTorch object detection model can understand during training. Okay, so this is a reason. That's why we create a custom dataset class, or you can say either you can change the name. It's we have to make this class also. Okay, so it's the reason it is this is the reason is this one, because we have to read it and convert that label annotation into tensor format. And then after that we have to use data loader, this data loader, to load this. How we can do connect this all classes and data loader, I will explain you here. So here we convert get the class. This function name will be have to be remain same, this init length and get item. Otherwise the data loader will throw the error, so that's why it's required. Then it's up to you that how you can use the parameter. It's parameters depend upon you, but function name has to be same. Okay, then self image directory we are passing here. Annotation means name of all the annotation file name present in a particular directory. Okay, then annotation directory. Transformation, you already know what is the meaning of transformation. Initially it will be none. Okay, then we have to initialize each you can say variable image, self image directory, annotations, annotation directory, and transformation. And whenever we use length function, then it will give the number of images present which is used for the training. Then get item here, with the index value we have to get everything. So how we doing that? After getting the index value, first we have to know the annotation file name. So for that we have to just use helper annotation idx. We get the annotation file name. After that, for getting the image path, we just use whether path join self to image directory and just convert last four digit with .jpg, because last four character of the annotation file name will be .txt. So we have to replace that. We do not want those last four character .txt, so that's why -4 here. And after that we just add .jpg. This way we get the image file. This way we get the image file name, and this whole thing give me image path. After that we read the image. If the image is not, then there's an error will be thrown to me during training. And then after that, you have to, you know, that we have read the image into BGR format, so I have to convert it into RGB. So here we are converting that. After that, we have to get the width and height. Why we have why we are using here width and height, I will explain you. Because let me explain later. So here, then after that, we have to know the annotation file also, because this give me this annotation file name. To what, here we have to get annotation file path. For that, we have to use os.path join self annotation directory, then annotation file name. This way we get annotation file path. After that, we have to make the two list, because we have to, for detection, we have to pass labels and boxes both for single image. So how we can do it? First, we have to read the image into read mode. Then uh, all data will be stored in this f variable. After that, we have to iterate over the f line by line. So here we get f line. And one more thing, that we have downloaded, you can say we have downloaded data set in YOLO v9 format, and the bounding box stored in this YOLO v9 format is in this format: x center, y center, box width, and box height. So how we can retrieve this? First, data is equal to line dot strip dot split, give me all the data present in that particular uh, uh, txt file. In that particular txt file, convert that into the list format, and all the data present that list is in character format. So we have to convert that into float. That's why, to get a class id, just use data 0, you will get a class id, and convert that into int format. After, to get the x center, just use data 1 float, then multiply with width, you will get the x center. Y center, just data 2, then you will get multiply by height, you will get the y center. Box width, data 3, multiply with, you will get the box width and height. Now we have to know how we want the data should be in a x min, y min, x max, and y max. X min, you can say, and y min will be the top left corner of corner bounding box coordinates, and bottom right corner of bounding box coordinates value. For that, just minus x center minus box width, means initially, for we have to box width divided by 2 initially, then subtract that with x center, you will get the x min. When you will box height divided by 2 and multiply subtract by y center, you will get the y min. And same way, after, for the x max and y max, we do addition here. Okay, so this way we get it. And just we have to append it in the boxes dot append. Okay, this boxes dot append, we have to append it in this. Okay, then we have to label, also we have to append the labels. In label will be this class index. Okay, class index +1. Why? Because zero index value is just for the background. You can see we are using coco data set. Here you can say we have zero index value already fixed for the background, then the person, then the bicycle, means to 88, 89, 19, 91. Total 91 classes is there. Okay, 91 classes there. So that's why zero index value is already fixed for the background. So that's why we add class index +1 here. Then we have to append it. After that, we are converting that into the tensor format. After converting in tensor format, it might be possible that transformation is applied by the user, so we apply it if any transformation is there. After that, we just make zip, means zip, or you can say produce one dictionary, boxes and labels, so that we easily fetch the details, box and label for per image. This whole thing is happening only on single image. Okay, this whole thing. Then we just pass the image and a target. So this way, this we create a class. After that, we have to load the model. So how we can load the model, and what is happening here? See, first of all, how many classes which we have? According to data.yml, we have a 3 classes, but for the SSD, zero index value is already fixed for the background. So actually we have 4 classes, including this 3 and 1 background. We have 4 classes. Okay, and let me close it now. And just we have to create this means call this function. Its size will be 640. Now what is happening here? First, load a pre-trained model, pre-trained SSD model, and the model which we use SSD 300 with BGG16 backbone. So this way we load the model. Okay, this is a pre-trained model, okay, which is trained on this coco dataset. SSD 300 BJ16 model is a version of SSD which is with a backbone version pre-trained on a Coco dataset. Okay, it's trained on Coco dataset. But let me print the model first. Now let me run it. What's the problem? Torchvision is not defined. I think so. Oh, I have not run this cell. Forget to run this cell. Okay, so this cell will take time. Wait for it. It's done. Now let me run this cell. Okay, after downloading, you can see this is this classification had this classification and regression had is not up to us because we have a 4 classes, but you can see here is according to 91 classes. This 364, 544, 446 and 546, and all this is done with according to number of 91 classes. Okay, so how we can change this? For that, first of all, we require the in channel. Why we require the in channel? Let me show you. So this is an image, and you can see the last layer of sequential for each sequential last layer is connected to this head. Okay, so last layer output channel, sequential last layer output channel act as a input channel for the head. So that's why here we call it a in channel. How we can compute that? So for that we use utils. I already told you utils dot retrieve out channel. Just pass the model dot backbone, then the size, and you will get the in channel. Okay, so let me print the in channel. What is this? Now let it does not. Okay, both things I have to print it just for the explanation purpose. Okay, see here where it is the in channel. See here it is a in channel. You can see 512 1024 512 256 256. According to this image, last layer of each sequential is active. Output channel we want to know. So here 512 from where it's come. Let me show you. Okay, so this is the first sequential. This is the first sequential, and here its last layer. This is the last layer, and its output channel is 512. So this is 512. Now 1024. After that, this is a second sequential, and here last layer is this one, and its last output channel will be 1024. Same way here, third sequential last layer output channel 512, 256, 256, 256, 256. So this way 1024, 512, 256, 256, and this last layer 256. So this way in out channel of each sequential last layer is act as an input channel for the head. So this way we calculate the in channel. I have told you the reason that why we have to calculate the in channel, and how we can do it, how these values are coming. Now we want to know number of anchor boxes. Now get a number of anchor boxes per location from the model anchor generated. This way for getting it we use model dot anchor generator dot number anchor per location. This way we get the number of anchor boxes for per location, or you can say per layer. Okay, explanation SD uses anchor boxes at different aspect ratio and scale. This line retrieve the number of anchor boxes. So now let me explain you how it's done, how it is happening here. Let me run it. So here you can see, oh sorry, now you can see that we have anchor number for first layer. Anchor will be 4 anchor boxes will be there. So here you can see how this calculation is done. 364, how it's coming. Let me explain you. We have 91 classes. Okay, calculator open. Here we have 91 classes in a Coco data set, and you can say for the first layer anchor boxes will be 4. So when you multiply 91 with 4, you will get 364. And second layer we have 6. So when you multiply 6 into 91, we will get 546. This is a classification, just for the classification purpose. And when we were coming for the regression hat, will be the bounding box regression hat. And in one bounding box, we have to calculate four coordinates value: dx, dy, dw, and dh. Okay, the four coordinates value we have to calculate. So that's why when you multiply 4, and first layer anchor box will be 4. When you multiply it with 4, you will get 16. And same way, and 16, second layer have 6 anchor boxes, and you multiply when you multiply 6 with 4, because 4 for the prediction of the bounding box, you will get 24. So these are the calculation are going on, but this calculation are going on with the 91 number of class, according to 91 number of classes. So we have to change it. So that's why we required in channel and number of channel. After getting it, we have to change the classification head. So this way we can change the model head, classification head, and we get it in channel. Just pass the in channel, number of packet, and number of classes which we have. And this is the second, this is the other thing. Okay, adjust the transformation size to match the input size, model transform min size and max size. This is what's happening here. But the main thing is that this is the main thing. Okay, this is a main thing. In channel, why we need a in channel, number of anchor, why we need it. Okay, and how we have changed the classification head according to our number of classes. So, and also I have also explained you the calculation how it's going on. So this way it's done. Now let me run this, and now let me print this new model. So after printing a new model, we can see the classification head is now changes according to our number of classes. We have 4 number of classes, including the background. And when you multiply it, because you know the list according to list, first layer have 4 anchor boxes. So when you multiply with 4 and 4 number of classes, we get 16. And second layer have 6 anchor boxes. So when you multiply with 6 into 4, you will get 24. And same way for a regression hat, you can bounding box regression hat. So this way it's going on. Now here we have to test train image directory, train annotation directory, and train annotation give me the list of all the text txt file name present at annotation directory. And here we're using a custom data set. We are passing the train image directory according to the parameter only you have to pass. Otherwise, during training it will throw the error. Okay, BFAS pass image train directory, then the train annotation directory. Transformation is just a transform to tensor. We convert all things in a tensor format. Okay, this is what happening. We have created the object of our class. After creating the object of the class, using the data loader, we create a data loader which generate the batch, generate all images into, or you can say convert all the images into the batches which is required during training. Okay, so this is data loader. So how it's doing, create a data loader that load training data in batches of 4, because I have batch size 4, shuffle the data each epoch, and uses a custom collect function to group image and target separately, are useful when sample have different size. Example in object detection. That's why use callback function. Shuffle, yes, we want to true it, batch size will 4, and just pass the train dataset object which we have created. So this way we have created a data loader which divide the images into the batches in 4 batches. In one batch 4 images will be present. So this way we require a data loader for which is important for training. Now when we want to know the length, it will give me this thing, how much image is present, 114. It's a so it is a LAN or a train data loader. When you multiply it with 114 multiplied with 114 is the number of patches. Okay, so total 456 images are present. Okay, now this is a setting of learning rate or optimizer. Okay, so first of all thing is select the CPU or GPU it's available. Okay, so for that we use if torch.coder is available. If it is available, it will be CUDA, otherwise it will be CPU, means device will get fixed. Then we have to pass the model to the device, whether it is CPU or GPU. Okay, then collect only the parameter that require the gradient update. We only want to collect those parameter which have a parameter which parameters are trainable. For that we use we iterate over the model dot parameter which we have created, And if p dot every parameter have one attribute p dot required grade, if it is true then p, otherwise it will do not be used. After getting the list of this all thing, we just pass it to the optimizer, because optimizer is responsible to update the parameters. Okay, so for that, SSD optimizer update model weight using gradient, learning rate control, update size, momentum, speed up conversation. Okay, update size. Okay, how much learning rate basically decide how much the weight value has to be increased, how much weight value has to be decreased. Why we have to increase or decrease? To ultimately decrease the loss. Okay, scheduler. What is the use of scheduler? Learning rate scheduler that reduce learning rate by factor by 0.1, where after every 3 epoch you can say toss dot of optim dot lr scheduler step lr. First we have to pass the optimizer, then step size 3 means after every third epoch you want to decrease value 0.1. This is what happening here. Initially the epoch 1 learning rate will be 0.01, which we have decided. Okay, so this is 0.001. After that this will not change, this will not change. After third epoch it will multiply it with 0.1 and its learning rate will be decrease. And after seventh, in seventh I again multiply by 0.1 and it will also decrease. So this way we learning require learning scheduler to decrease the learning rate value. Okay, so that it decide the rate, it decide the, we can say, rate control update size. Okay, it's control the rate of the update size of the update size. Okay, this is what is we have decided here. Initially the number of paper will be 10. Now this is just, you can say, we how we can use the data loader to visualize the images. How we can do that? This is what happening here. Let me explain you. Initially we want to plot 16, we only want to plot two images. For that it is one row and two column. Figure size will be 10 and 16. You can see plot the subplots. One means one row, two column means two images will plot. Figure size will be 10 and 6. And axis, initially it is a in 2D format here, and figure basically representing the entire subplot. Axis dot really converted into the 1D format, which is easy for the iteration. Now to get the images and you can say targets, we have to use first we have to create the iterator for the train data loader. When we use next, it give me images and target of first batch. In this, images will be four images present. Target contain four images, label and boxes. And number of classes which we have, including 0 for the background, then a chair, then a sofa, then a table, and each class have unique colors. That why we use CMI color for color sample. Now to for plotting of two images, you have to iterate for the two time only. Okay, for idx image, idx means zero index value dot permute dot numpy. What is this? Convert the dot permute 1 to 0, convert the chw, convert from chw to hwc for visualization. Okay, we convert the, when we convert the when we do this tensor, when we do the transformation to tensor, it basically convert the channel from hwc to chw. But for the plotation we required the hwc. That's why we use permute 1 to 0. Okay, then target idx give me target. When we use target boxes dot numpy, because target is a dictionary, so when we use target dot boxes dot numpy, give me boxes. Then target labels give me labels for each image. Initially you can say I am so image, then it will plot the image. And for the plotation of the boxes, we zip over boxes and label at the same time. Okay, it for per bounding box coordinate value, give me the label. Okay, then this is xmin, bymin, xmax and bymax. And we are plotting this for using a subplot, using a Matplotlib. We are plotting the rectangle. For that we use patches dot rectangle. Then we just pass the xmin, bymin, width and height. Line width will be 2, edge color will be decided by the color sample. Label -1. Why minusing 1? Because zero index value is for the background, so it will be level -1. Okay, then face color will be known. Then here we generate a patch of the rectangle. To add this patch in a image, we just use idx dot add patch rectangle. It will add the rectangle patch. Then this will be add a text, okay, over the, you can see this like this. We add a text, this is x mean. This is the, you can say, coordinate value, or where we plot the, you can say, uh, where we plot the text. We want to display the text. The class name will be label. Just pass the label. You will get the uh, which what is the class label of that particular object. Then the color will be k. Then font size will be 12, and bounding box detail. This is what be happening here. Okay, this is what happening here. Bounding box. This is a bounding box around this. You can see that. Around a text one bounding box line with it, this is that line. Okay, hope you get understand. Let me write it now. See, chair screw working well. Now this is a training part which is important. Okay, for that we use tqdm, which is to make it visible the line. Okay, so how we can do that? Just use how much epoch, 10 epoch for epoch in range number of epochs. Then we number of epoch we have to iterate according to the first thing which we display is starting the training of epoch plus one. This line will get display. Now it is important that model should be in a training time train mode. Okay, not in an evaluation mode. So that's why model dot train we have to use it. Now initial training running loss will be 0 0. Okay, now we have to apply the tqdm. For how we can apply the tqdm, just you train data loader, then total length of the train data loader, then the dsk, then what we have to display. This is what we want to display on the line. Okay, so this epoch 1 divided by 10, this line is decided by here. Leave true, yes. Okay, now just after that, you this variable which is we have created, we have to use here. It will give us images and targets. For first iteration, we give me batches. After that, give me the batches. So we have to make sure that a model and images and devices all things should be, same device. So this two line decided, or we can say work like that, means it will place images and target all in a single device, and a device which was selected whether it is cpu or gpu. Now we just pass the images and target both thing. After that, forward pass will be this line is a forward pass. After that, how we can calculate the losses? Total loss will be sum of all the components. So for that, we loop over the loss of dictionary. Okay, here we're looping over the loss of dictionary and getting the loss. After that, we sum up. This function give me the sum of this, give me the losses. So after add all type of losses will be added here, and we'll get the sum, and all this variable will store this here. All thing, this proper whole thing is happening only for one batch, not for the one image. This whole thing will be happening for the one batch. Okay, so this is a method, we can say, formula which we calculate new weight. So new weight calculated by the old weight minus the learning rate into the gradient. Okay, now what is gradient? Gradient tell how much and in which direction a weight should change to reduce the loss. Okay, so what is this optimizer zero gradient, and why we doing it? What is the use of this? Clear previous stored gradient value, or you can say making the previous gradient value to 0. Why are we doing it? Because if we do not do that, then previous value of the gradient will accumulate to the current batch gradient value, and it disturb the weight updation. Okay, new means weight value will not get properly updated. So that's why we initially optimize the zero grade will make the current gradient value will be 0. After that, losses dot background commute the gradient value according to the loss. It will commute the gradient value. Here just the calculation is happening, not the updation of the weight will be happening. Okay, now that optimizer dot stab will update the weights. Okay, so here initially we done make the gradient value 0. Here the computation of the gradient value will be decided. Here the updation of the weight value happening. After this whole happening, we batch loss will be losses dot item. We calculate the batch loss. Okay, I'm just talking about the single iteration. So here we got get a batch loss, which we accumulate or add in a training running loss. This here in training, in this training learning loss. Okay, after that, scheduler step means step learner mid scheduler after epoch only, because this will happen after third epoch only. With learning rate value will change, so that's why it should be outside this for loop, inside this for loop and outside the this for loop. Scheduler dot step. Now after we can say after one epoch it will get completed, we want to display the loss. For that, to display the loss, this is a calculation which we have done. Okay, epoch loss, this way we calculate the epoch loss, and which we append in a training loss. This is a list which we have used, which store every epoch loss value. Okay, so this that's why we append it to epoch loss, and this will display it. Now let me run it. I think so I have explained each line what it's mean and why we doing it. Okay, so here is training going on. Now let me explain you this. After that, we store the model. So how we store the model? This is a line through which we store the model. Okay, torch dot stay save model dot state dict ssd dot custom dot ssd custom dot pth. So this way we store the model. Now how we load the model? For loading the model, these are the libraries which we use. Okay, now to here also we have to load the pretrained model. So how we do that? Okay, so this is the device, same thing line. Make sure create model, give me the model. Okay, according to our number of classes, but we have to load the model which is trained on custom data set. So just use this model. This is here it give me architecture. Here it's give me the architecture of the model. Now we have to load the weight file. For that we use model.load state.tick torch.load the model which we have saved. So here this line will load the model which we have saved. Now here the model is not in a training mode, so here it will be in an evaluation mode. So that's why model.eval, and we just pass the model to the device which we have, whether it is a CPU or a GPU. After that we want to plot the 16 images. For that we use same thing. I have explained everything, just 4 rows and 4 columns. Everything will remain same. Now transformation dot to tensor, it's required because before training we apply some transformation to the images, which is this one. And it's important that during evaluation you have to apply same transformation, otherwise it will throw the error. So that's why transformation to tensor, then we have to apply it. Then this is a test directory. Then we have to OLS directory, means all the images name present in that particular directory will be stored here in this list. Initially the labels will be same thing, same, everything will be happening the same. We select the image path. Okay, where the path join test directory, then the randomly select the image name, and this way we get the image path. After that we open that image and apply the transformation over it. Then we just unsqueeze add batch dimension. It's required because you can say during training here everything which we are passing here in the batch formats, so it should be compulsory that we have to add one batch dimension to the image. So what adding the batch dimension, you have to use image dot unsqueeze 0 to device unsqueeze till here. Then we have to pass the image to the device which is and on which the model is same device. So that's why this is happening to a device. So unsqueeze basically add one dimension to it. Okay, then with torch no gradient prediction, just pass the image which we have, and to get we are passing the single image. To get the result of that we use 0 index value. After getting the prediction, this is what is happening here. Convert image to numpy for visualization. Okay, as soon as we apply the transformation to it to the image, it's the dimension from HWC, it's converted to CHWH. But for the visualization purpose, we again have to convert that CHW to HWC. For that we use image, just that CPU. We have to come back. We have to make sure that the image should come back from GPU to CPU. Then apply the permit which convert the CHWC, and it's convert to numpy, because it's in a tensor format, so to convert it into numpy. Then how we get the boxes details, prediction boxes dot CPU to numpy, then the labels, then the score. This way we get all the values. Now one by one. We have to zip all this and we have to add it over one, all these values one by one. Okay, now here we're showing the image, then the access will be off. Image dot open image path, it's not oh, we have open it. Okay, image and p, where image and p we are showing it. And why we have done it here, image, it's not used here. I think it's not compulsory, it's extra line. Now how we are applying the bounding boxes. Okay, how we are applying it, just you can see that we are zooming, for loop is apply on boxes label and score. So at the same time, for one bounding box it give me score also and label also. Okay, then how we can select the color sample, just label -1, give me the color value. If the score is greater than 0.8%, it means then if the bounding box coordinate confidence value is greater than 80%, then only we draw the bounding boxes around on the image. So that's why we, how we get it, box x min y min x min y min, we get a value. But for the rectangle patches we require the width and height. For that we calculate the width and height here. Then how we added the patches, just use patches to rectangle, just pass the x and y min, width, height, line width will be 2, edge color will be 12. Edge color will be this one which we have done, and face color will be none. So this way we make the patches. Now how we want to add it, just use access.ids add patch, patch will be added, and this will be display the text. Class name will be label, just pass this label which we have got, and class name will be get a text, and this way we display it. I think so our training gets completed. Yes, our training got completed. Our model also that store is also, you can say this is a model which is stored here. Now let me run it again so that we can show the result of the model which is trained on TinyPop. I think so it's working very well on TinyPop also. Okay, this print statement is because we have done some print during explanation. I printed the statements there, so that's why I'm showing this one. So okay, completed. So this is the result we get. Chair, I think so most of the images are belong to chair also, chair only, and sofa. Okay, chair, sofa, I think the most of the images are present here of chair and sofa. Table images are less, so that's why the table images are not coming. Okay, so this way we can do create a train a SSD model on a custom data set. Okay, and we can download this model and use it anywhere you want to add. I have explained each and everything line by line, so please like, share and subscribe my channel. Thanks to all.